Um, Welcome everyone to the 142nd meeting of New Directions in Group Theory and Triangulated Categories. Our speaker today is Paolo Tomasini from Luxembourg, and he'll be talking to us about elliptic Hochschild homology.
Thank you very much. Thank you very much for the invitation. Let me just share my screen quickly. Okay, you should be seeing it now. Excellent. So today I'm going to report on some joint work with subsets of Christian Forero-Pulido, Sara Scherotzke, and Nicola Sibilla. So this is the tentative plan of my talk. So I will go first through some motivations coming from topology, and then I will go through a review of the ideas introduced by Moulinos-Robalo and Toen about twists of Hochschild homology. And then I will go through some constructions to enhance some versions of these objects to equivariant situations, and then some universal constructions over the moduli stack of elliptic curves. Okay, so let's go first through the introduction. So some main ideas from topology that we are interested in is, for example, that for a topological space X, we have families of invariants called cohomology theories. And among those cohomology theories, there are some that have certain niceness properties. In particular, we'll be interested in some very specific ones that share the following two properties. So first of all, they are complex oriented. Which, roughly speaking, means that they have a nice theory of first Chern classes of line bundles. So more precisely, this means that if you compute for one such cohomology theory, well, if you try to compute this cohomology theory on CP infinity, there will be an isomorphism with the cohomology of the point adjoin the form of variable t in degree 2, and the complex orientation will be a choice of such variable t, choice of such an isomorphism. And you should think of this variable t as being exactly the first Chern class of a universal line bundle, the tautological line bundle living on CP infinity. So somehow this is the first niceness property that we want for our cohomology theory. There will be a second one that goes under the name of even periodicity. So one such cohomology theories will have the property that for the nth cohomology group of the point, this will be isomorphic to the cohomology group in degree n-2. And this isomorphism is implemented by the existence of some invertible element in A-2. And this is somehow the periodicity aspect. And then we have the evenness aspect. So whenever we compute the odd cohomology of the point, this will vanish. So this is a nice subclass of cohomology theories. And indeed, the the niceness of it is captured completely by the important theorem of Quillen, which I state very informally. So the idea is that there exists a relation that links these types of cohomology theories with, let's say that the cohomology of the point is a certain ring R. Well, these cohomology theories are linked to one-dimensional smooth formal groups, which are abelian and live over the ring R. So the idea behind this relation is that if we take our cohomology theory A and we compute the cohomology at CP infinity, taking its formal spectrum will yield not just a mere formal scheme which looks like formal completion of A1 at a point at the origin, let's say, but rather a formal group, because CP infinity is equipped with some kind of multiplication map. This is a formal group. Thanks to the map CP infinity times CP infinity to CP infinity that classifies tensor product of line bundles. Similarly, we can hope to go back from some formal group G, which is smooth and one-dimensional over R and abelian. We may hope to go back to some AG, complex-oriented event periodic cohomology theory, but this will require certain extra assumptions go collectively under the name of Landweber exactness. From here, we are not very much interested in the specificity of this relation, but rather in the philosophy of it. So one-dimensional smooth formal groups, abelian over a certain ring R, parameterize certain types of cohomology theories. So some nice cohomology theories over R. So we want to take this philosophy and import it into algebraic geometry. So somehow the key idea for the rest of this talk will be, we are interested in what we want to bring this picture to algebraic geometry. So now with this in mind, we can go to the next part, twisted Hochschild homologies. So the main idea is due to Moulinos-Robalo and Toen. So similarly to Quillen's theorem, if we are given one such formal group, that just to simplify the language, I will just call formal group, but I will always mean one-dimensional abelian formal group smooth over R. Given one such object, we want to cook up a deformation or a twist of Hochschild homology. So as a preliminary, let's go back to traditional Hochschild homology. Let's see how to interpret it in terms of geometry. So let's start a detour on Hochschild homology. So the usual setting is for some not necessarily commutative, let's say associative algebra. And let's say that we are working over K field for simplicity, but absolutely not necessary. We can define the HH of A, and from now on, I will probably forget the little dot downstairs. This we can define as the following product. So we are essentially taking the tensor product of A with itself, viewing A as a bimodule over itself. So with this in mind, we immediately forget the fact that we can work with algebras that are not commutative because we want to slightly start moving towards geometry. So first thing to do is to assume that our A is commutative. Then the definition of HHA slightly simplifies. So let me also forget to write L on the tensor product and just always denote my tensor products as derived. So now the formula for HHA looks slightly simpler. And now it definitely can be interpreted geometrically. Because let's say that I take the spectrum of A. So let's say that I take spec of A and I take its intersection with itself over the diagonal. Now, of course, when I do this, I am implicitly using some kind of derived fiber product here. Otherwise, I will just get back spec A. But assuming I can do this without any particular difficulty, so let's say that I use some derived fiber product. Whenever I take global functions on this object, I'm going to simply recover HH of A. Because I'm just going to define the fiber product as usually we do. As by taking the spec of the tensor products. So the third intersection of the diagonal is our geometric interpretation of Hochschild homology. Now we can do something slightly better. So let's say that I want to take maps from the following object. So I take 2 points, and then I take the disjoint union over 2 different points. And I map this into spec A. No, this is a coproduct. This is a colimit. So when I map into some object, it will transform into a limit. And it is exactly the limit that appears above. And if I allow myself to take my my co-limits in a homotopical sense, then what I'm actually doing here is I'm taking the suspension of S0, which is just the pair of two disjoint points, which is S1. So what I'm actually doing here when taking the self-intersection of the diagonal is I'm just taking maps from a topological circle into spec A. So what usually people call this is the derived loop space of spec A. And by what we said before, if we take global functions on loops of spec A, we get back Hochschild homology of A. So with this definition in mind, with the traditional definition interpreted this way, we can extend the notion of Hochschild homology to any stack. And we do this way, so in the most obvious way possible. So for any stack X, we can define its loop space by taking maps from the topological circle into X. And then we define the Hochschild homology of the stack to be the global functions on Lx. So this is the geometric interpretation of the traditional Hochschild homology and has some important properties. For example, the main one we are interested in right now is the following, I will report it as the following theorem due to Hochschild, Constant, and Rosenberg. But I will present it in the form that it is cast by Bensby and Ladler. So if X is a scheme over a field K of characteristic 0, we have the following isomorphism. So the loop space of X is isomorphic to something called the shifted tangent bundle of X. So the loop space was the self-intersection of the diagonal. The shifted tangent bundle is the self-intersection of the zero section of the tangent of X. So this guy, the X minus 1, is obtained as the fiber product of X over its tangent, where the map is given by the zero section. Okay, so this is somehow what happens over a field K of characteristic 0. And in this situation, the hypothesis of being in characteristic 0 is fundamental. So let me give you an idea of why this theorem is true. So we can identify these two objects passing by a third object, which is usually denoted by LUX, meaning unipotent loops. This is maps from another stack called the BGA. Somehow we have a triangle of objects that are all isomorphic to them, to each other. Here, BGA should be thought of as a formal version or very, very small version of S1. Or rather, what you should think of this is as an analog of the dual numbers kt mod t square, where we replace the variable t with a variable in the cohomological degree 1. Okay, so somehow a very fundamental aspect of that makes this equivalence work is the following. So over k of characteristic 0, we have an equivalence of the affinization of the circle, that is the spectrum suitably interpreted of the cochains on the circle with coefficients in k with this object BGA, which is just the spectrum of this algebra k epsilon, where epsilon is a variable in cohomological degree 1. Here spec has to be interpreted suitably. These objects are not affine schemes, but rather affine stacks. As defined by Toen. But what really matters to us is that in characteristic 0, the circle behaves like this BGA whenever we map into a scheme. So the fundamental insight that was brought forward by Moulinos-Robalo-Toen is that you should interpret this isomorphism of the affinization of S1 and BGA as being some incarnation of the exponential map, identifying the formal additive group with the formal multiplicative group. This map is only available to us when we work over a field of characteristic 0, because we need to divide by all numbers. And you should think of this equivalence between affinization of S1 and BGA as an incarnation of this object. So in general, you expect HKR to fail when K is not of characteristic 0 and be replaced by some more complicated type of statement. And more importantly, what you expect as a side effect of this is if you work over general rings, you will not have an equivalence of the loops and the shifted tangent bundle, even for schemes. So their insight is that you can define a version of the loop space that depends on a formal group. And this is their definition. So given G a formal group, over some base discrete ring R, we can define a G-twisted circle as the classifying stack of the Cartier dual of G. Which is the group of characters of G, and it is an affine group. And with this twisted circle, you can define a twisted loop space given by the maps from the twisted circle into X. For X, an affine scheme. And once you have a notion of a twisted loop space, you can cook up a notion of twisted Hochschild homology by taking a global functions on this loop space. Okay, so this is the fundamental insight of Moulinos and Robalo-Toen. Some years later, joined with Nicola Sibilla, we gave another definition. Before that, let me stress that at the very end of their paper, where they define these objects, they in particular stress their attention to a very specific example that might be very important. So if G is obtained as the formal completion of an elliptic curve over R, this gives rise to some E hat twisted Hochschild homology that they called elliptic Hochschild homology. So they claim this is a very important example, of course, because it wants to be related to its topological counterpart, that is elliptic homology. Which is the cohomology theory associated to the formal completion of the elliptic curve under Quillen's theorem. So given the formal completion of an elliptic curve, we can cook up this elliptic Hochschild homology using Moulinos-Robalo-Toen's recipe. And we want to think of this as an algebraic analog of elliptic homology. So as I was mentioning, sometime after that, because this is so Moulinos-Robalo-Toen's definition appeared on arXiv around 2019, while the next definition appeared around 2023. And this is based on a joint work with Nicola Sibilla. So let's pick E an elliptic curve over R and X a scheme over R. So we define map 0E X to be the connected component of the constant maps from E to X in the mapping stack from E to X. Now, with this definition, we call HH lower E of X the global functions on map 0 EX. And we call this, again, elliptic Hochschild homology. So when we came up with this name, we were not aware of the existence of the thing above. Otherwise, we would have not chosen the same name. So somehow something was needed in order to fix this issue of having two different things with the same name. And somehow there is the intervention of a third person saved us from this impasse. But before that, let me state a couple of properties of this definition. So let R, now my base ring, be just a K, a field of characteristic 0. Then we have something that looks like a HKR for map 0. So for X over the scheme over K, map 0 EX is equivalent to the maps from the affinization of the elliptic curve to X. Now, similarly to the case before, the affinization of E is a spec of its coherent cohomology. So this O of E is the derived global functions on E. And the cohomology of this object, which is a complex, is given by the cohomology of E with coefficients in its structure sheaf, so the coherent cohomology of the elliptic curve. And you know this is your base field both in degree 0 and in degree 1. So it looks like the cohomology of S1 over the base field K. In particular, there is a non-canonical isomorphism between the affinization of E and the affinization of the circle itself, which composed with this isomorphism above gives an isomorphism map 0 EX with the loop space of X, which you can think of as an elliptic version of HKR. So according to the philosophy that we had before, we expect some kind of failure of this phenomenon in non-zero characteristics. So this is something we did together with Sarah Scherotzke. So over, let's pick E an elliptic curve. Over R and X scheme. Then the first statement is that the affinization of E over the ring R is actually equivalent to the Moulinos-Robalo-Toen circle twisted by the formal completion of E, viewed as a formal group. And in particular, this implies that for every scheme X, the Hochschild homology of X twisted by the formal completion of E, so this is the Moulinos-Robalo-Toen elliptic Hochschild homology. This is equivalent to the elliptic Hochschild homology as defined by Nicolas and myself 4 years later. So I will give you an idea of how this theorem works. So the fundamental base result that this theorem is based on is the following proposition that is in the same paper by Sarah, Sibilla, and myself, where for G some formal group over R, we can consider the quasi-coherent sheaves on G viewed as a stable infinity category. We can equip this with the convolution tensor product, and this will have an equivalence with quasi-coherent sheaves on the Moulinos-Robalo-Toen twisted circle, equipped with a standard tensor product. So we call this Fourier-Mukai equivalence. We call it this way just because it intertwines the convolution monoidal structure on one side and the standard monoidal structure on the other side. So it is slightly a stretch of language. And this proposition depends on the fact that you can identify these two categories with a third category that sits in the middle. And that's the category of comodules over the distributions of the group, equipped with a standard tensor product over R. So here the distributions are the global functions on the Cartier dual of G. And you can identify separately the two categories above with the category of comodules over this coalgebra. This is naturally both an algebra and a coalgebra. And this Fourier-Mukai equivalence allows us to construct, just following the equivalence, an equivalence between the functions on S1 associated to the formal completion of E and the functions on the affinization of E, by composing with the standard Fourier-Mukai for the elliptic curve. And this equivalence can be lifted with some work to an equivalence of the stacks themselves. Because as I mentioned, those are affine stacks, and maps between them are detected by the maps at the level of global functions. Okay. So this fixes the language problem of having two things which look different but have the same name. Nevertheless, the definition that involves map zero has one slight advantage over the definition given by Moulinos-Robalo-Toen, and is the following one. So this involves moving to the equivariant situation. So let's say that now X is replaced from a scheme to a stack. So the case that we will be interested mostly in is a quotient stack where Y is a smooth quasi-projective variety, over K, a field of characteristic 0, usually just the complex numbers, and T is an algebraic torus. So this is the situation to keep in mind basically always when for the rest of this talk. So we can consider map 0 from E to such X even when X is a stack. Now, for this to make sense exactly and to reproduce what we want, that I will explain later, this requires a slight enlargement, slight modification of the definition of map 0. To account to the fact that we don't always want map 0 to be connected. But in most cases, it will be fine for it to be connected. So I will not describe what this modification is. Now, notice that in general, for X a stack, taking maps from the affinization of the elliptic curve into X, this will differ from the maps from map 0 from E to X. So there is some meaning to considering this map 0 against stacks and not just maps from the affinization. So with this, we can slightly refine our notion of elliptic Hochschild homology in the special case of a quotient stack. So now let's really consider mapping to Y mod T with Y and T as above. We will have a natural map to the space ET, which is the coarse moduli space of degree 0 T bundles, principal T bundles. On the elliptic curve E. And let me call this map P. We want to make the following definition. We call Schiffy elliptic Hochschild homology, and denote it this way, of the quotient Y mod T, the push forward of the structure sheaf. Viewed as a quasi-coherent sheaf on this space. And we do this motivated by the definition of equivariant elliptic homology. Due to Grojnowski. So the main motivation for our definition to look exactly like this is that, and somehow this object was originally meant for exactly to recover this the equivariant elliptic homology. So this is done via by recording some extra data. So let's the following remark. So when we consider the maps from E to any other stack X, as a stack, this mapping stack has an action of the elliptic curve. And this action allows us to define a sort of Tate construction. It allows us to define a periodic cyclic version of this theory. So this is done in a way that mimics the construction of, so this mimics the construction of periodic cyclic homology from Hochschild homology. And crucially rests depends on the fact that the affinization of the elliptic curve is isomorphic to the affinization of S1. So usually periodic cyclic homology is obtained from Hochschild homology by recording a certain S1 action. And what we are claiming is that the elliptic curve, what we can prove is that the elliptic curve is close enough to a circle to allow you to define a Tate construction, and thus a periodic cyclic homology. I will not go too much into the details of this construction, but I want to tell you why this construction is relevant. So together with Nicolau, what we proved is that the periodic cyclic homology of a quotient stack of y and t as above, this will recover the equivariant elliptic homology of the analytification of y. So here we are working over C. And this is the equivariant elliptic homology as defined by Grunowski. So as a sheaf over this space ET that I talked about before. So this is some kind of elliptic analog of a series of results that were due to many people, Kalak, Pantev, Toen, Bakiem, Vetsosi, in the context of the shifted tangent bundle and Alper-Neistener and Pomerleano in the context of the loop space, that all sort of fit in the same framework. So when you take a periodic cyclic homology based on the shifted tangent bundle, I will not be super precise, I will just call this HPGA, of a quotient stack, this will recover the equivariant cohomology of Y. And this is due this is a consequence of work of Kalak, Pantev, Toen, Bakiem, Vetsosi, so the first group of people that I mentioned. And on the other hand, if you take just the standard periodic cyclic homology, that is based on the loop space, because it's based on standard Hochschild homology, this will recover the equivariant K theory of Y, analytified. And this is due to Alper-Neisner and Pomerleano. So you should think of this as the equivariant versions of the statements that we had before for Hochschild homology twisted by various formal groups but in this case, we are in the equivariant setting, and we are upgrading our statements from Hochschild homology to periodic cyclic homology, which turns our theories into some topological theories. And indeed, this is somehow the content of these theorems. So I will conclude by giving a quick overview of a universal version of these ideas. This is all joint with Christian Forero-Pulido. And the idea is to replace a single elliptic curve with the universal elliptic curve. Over the moduli stack of elliptic curves. This is sort of customary in the topological situation. And we just want to import those ideas into this setting. So the first fundamental definition is to just consider map 0 relatively to the base stack of elliptic curves from the universal curve to some x. This x will usually be just a scheme or a stack over some base field k, and we will then spread it over the moduli stack of the moduli of elliptic curves over k. So here I'm always considering everything to live over some base field k of characteristic 0. And then we can play the same exact game. So we can just define some universal version of HH. I will state it directly for a quotient stack of a projective quasi-projective smooth variety by torus. This will be some push forward of the structure sheaf of the relative mapping stack to a base, which is a relative coarse moduli space of T bundles of degree 0 on the universal elliptic curve. So what that is if you take T to be a torus of rank n, then this coarse moduli space is just a product of the universal elliptic curve with itself over the base moduli of elliptic curves n times. And this object has an associated universal version, which is periodic cyclic. And it has some good properties. For example, it restricts to any HPE or HHE for a fixed elliptic curve. So it really behaves like a universal object. So you can pull back this sheaf from the whole moduli of elliptic curves to a specific one, and you will get the old version of elliptic Hochschild homology or periodic cyclic homology for that fixed elliptic curve. And it does something, for example, quite nice. So you can do the following definition. You can define the global sections over the moduli stack of elliptic curves of this HHE of Y. So here we are assuming the group T to be trivial. So we are forgetting about equivariance. We can take these global sections, which now naturally live over ML. And taking global sections, we get some object that we can call HHTMF. And similarly, we can take the global sections of the periodic cyclic. Oops, sorry, I used the wrong notation here. I wanted the universal one, of course. And call this guy the periodic cyclic TMF homology. And for example, one computation you can do is to consider the HP TMF of a point. And this is not a difficult computation. It recovers up to taking this object will be a complex. You can take its cohomology. And if you take the cohomology of this, you will get a ring of weakly holomorphic modular forms. With coefficients in your base field, let's assume that it is C. So this is the type of object the type of thing you expect from the topological side when you take these TMF constructions. So it sort of behaves similarly. Okay, very well. I think this is all I wanted to say about these objects. So thank you very much.
Thank you, Paolo. Let's all give the speaker a round of applause.
Thank you.
Right, so if you have any questions, please ask them. I had a question, but it was, I mean, it's really not a question, it's a meta thing. I mean, I remember some years ago hearing some people talk about this thing of Lurie in the elliptic cohomology world, this tempered thing. Tempered, I mean, is there an adequate notion for temperedness in your elliptic Hochschild homology?
Yes, I don't have a complete answer because I have not thought too much about it, but it's possible, and somehow I'm just thinking about it right now. So I appreciate the question quite a lot, I have to say. So the idea is that you can take tempered versions of this. So the idea is that now you replace your formal group G with some p-divisible group. Let's call it GP. So here you are sort of fixing a prime in the background. And you want to use, like what you want to do is to define some S1 GP and then HHGP. So here the idea is like from the topology side, the idea is that if you have a formal group, this should give rise to a cohomology theory with the properties that we know. And this would be good for spaces, for topological spaces. If G is a p-divisible group, this should give rise to a cohomology theory that upgrades to a cohomology theory that is equivariant for finite groups. So this is the tempered cohomology. And if G is the formal completion of an algebraic group, this gives rise to a cohomology theory that can be defined equivariantly for any Lie group. So this is the topology side. And the algebraic geometry side would be that to a formal group, you associate a twisted Hochschild homology that makes sense for schemes. To a p-divisible group, you will associate a Hochschild homology that makes sense for X at the minimum for stack. So not just for any scheme, but rather some scheme modulo finite groups, or things that look like gluing of these things. And if G is a formal completion, you can associate a HH G hat that you can plug in Artin stacks. So for example, in the elliptic situation, you are in this case. And in fact, you can define something that makes sense when you plug in a quotient by, say, a torus or something, or some reductive group. So the tempered situation would be this one. And for example, there's some recent work of Mauro Porta with Sara Scherotzke and Nicola Sibilla and some other collaborators, where they define, where they look at the loop space of the Riemann for stacks. And they prove this is equivalent to the shifted tangent bundle of the inertia. This is the inertia stack. And you can somehow interpret this thing, which is the HKR for the Riemann for stacks, in terms of these tempered versions of loops. Because a p-divisible group will split in two parts. One is a purely formal group, and one is an étale group over the base. The formal group will be like the étale part will give rise to the inertia of X. And the rest will be in characteristic 0. The formal part is just giving rise to the shifted tangent bundle. Essentially, this is the idea fundamentally.
Okay. So it does make sense in this setup. Okay. Yeah. Any other questions? And also, I mean, because you guys have so many papers together, is all of this in one paper that's already out, or is some of it out and some of it is still?
There is a mix of things. I forgot to mention everything that I'm doing with Christian is all work in progress. So this is all work in progress. Everything else is subdivided in two papers. One is just with Nicola, and the other one is with Sarah, which I mentioned here.
See. Yeah. Sorry, yeah.
Yeah.
Okay. If we don't have any more questions, let's thank Paolo once again, and especially because he agreed to step in at very short notice. Nicolo was supposed to be the speaker today, and then there was a change of plan. Yeah, thank you again.
Thank you very much. Thank you.